Ready for this? I'm Joseph Shaw. I'm a professor at Montana State University and the director of the Optical Technology Center. Well, my work is more in developing optical remote sensing instruments, but it also includes the science of explaining natural optical phenomena. Auroras would be one of those things. The aurora is an optical phenomenon that is formed when charged particles come streaming in from the sun and get captured by the Earth's magnetic field. And then those particles collide with molecules of gas in the very outer reaches of our atmosphere. Those energetic reactions are releasing colors of light specific to the atoms and molecules that are releasing the light. All right, so we're going to look at questions that were submitted by social media readers, right? So the first one here that I have is, will the auroras move as the magnetic North Pole moves? Certainly yes. As our magnetic North Pole moves, so does our magnetic field. But, does that mean that the aurora will stop appearing in Alaska and start appearing more in Kansas? That would require a really radical shift of the pole. So no, it's not going to go that far, at least as far as I know. But there is a movement that will occur, yes. All right, next question. What is the best way to spot the northern lights from Gallatin Valley? I love that one, and I'm actually working on a book on exactly this topic. The best way to know to even look is to look at satellite data. There's just such a wealth of data on the internet now. So spaceweather.com is one that's run by a colleague of mine, and the NOAA Space Weather Prediction Center is one that I monitor, but that's much more sort of scientifically oriented. There are other apps that you can download on your cell phone that'll send you push notifications when the conditions are right also. But there are times when everything is right and all the data suggests that we should have just a screaming aurora, and I go outside and there's nothing. That just, Mother Nature is more complex than a 2-parameter model. And then what's the best way to spot them once you know that you could be possibly seeing them is you got to get away from lights. Light pollution is your enemy when you're trying to see the aurora. What that really means from a Bozeman perspective or a Gallatin Valley perspective is you're best probably to go north of the city. So we could all go south of the city to Hyalite, for example, and Hyalite is a great dark sky location. But then you're looking north over the light dome from Bozeman, and so that can impair what we see. It's mainly a thing about getting away from the lights and then letting your eyes get dark adapted at least a little bit. So if you're going to see the aurora, you got to stay up a little bit. A lot of times, if it's going to happen, it'll start happening around 10 p.m. or whenever our sky is getting good and dark. And one unique thing about being in the mid-latitudes is we can actually have summertime aurora. And actually, summertime tends to be the best time to see auroras in Bozeman, partly because that's when our skies are the clearest also. Okay, here's a fun one. Is there a limit to how far south or north the Aurora Borealis / Australis can reach? And so I will reword that. I think this question is asking, is there a limit to how low a latitude the aurora can reach? There is a limit, but there's not a limit in such a way that I can say the number. It's not like, it'll never get farther than this. That's just impossible to say because the physics is so complex. And who am I to say what Mother Nature can do, right? I can tell you probabilities. So if you went to 65 degrees north or 65 degrees south, that's kind of the optimal position to see the aurora. When you start getting down into that 40 degree, 38 degree kind of latitude, it's going to take a really strong storm to push the aurora that far into the mid-latitudes. But it happens. But it doesn't happen very often. So let's see what else we have. Do different particles in the atmosphere affect the aurora's colors? Not so much particles, but different atomic gases. By and large, the atmosphere, especially the upper atmosphere, is oxygen and nitrogen. And the colors that those molecules emit when they are excited are by and large reds and greens and blues. We are very sensitive to green light as humans, So the green aurora is usually what you see the easiest and the first. That's emission by oxygen molecules. Much harder to see is red. And there's red lines that are emitted by both oxygen and nitrogen. And interestingly enough, both oxygen and nitrogen, but especially nitrogen, has a combination of red emission lines and blue emission lines. And what happens when you mix blue and red together? You get purple. And so once in a while, we'll see just the right amount of blue emission and red emission so that we get a very purple looking aurora. That's beautiful. And I've only seen a couple times where that's sort of the dominant color. Okay, this is another good question. What research is being done at MSU about the Northern Lights? What are the opportunities for students to get involved? Let me answer the last question first. At MSU, we obviously are student-centric, but even more so than maybe you might guess, because as a Carnegie R1 university, which means we're in that top tier of research universities, you might expect that undergraduate students would not have much opportunity to get involved in research, because that's typical at R1 kind of universities. But at MSU, we really have a different philosophy. We have a culture, if you will, of student research, and we use undergraduate students all the time in our research projects. So there are lots of opportunities for students to get involved in research across campus. But now I'll address the first question, which is what research is being done at MSU about the Northern Lights. So there's a lot of solar physics, there's a lot of space physics, there's a lot of upper atmospheric physics going on, but there's also work in some of the engineering departments. So for example, in my research group, we have built a series of optical instruments that are meant to be aurora detectors. And those instruments have been built by mostly undergraduate students at MSU. And we've taken them to Alaska to test them under Alaskan conditions, and we've brought them here. Okay, this is one that I was hoping we'd get, because this is one I really need to answer. Why can you see the Northern Lights better through a camera versus with your eyesight? It all boils down to integration time. And what that means is how long you collect light before you read out the image. So we have rods and cones. The cones give us color vision when we have sufficient brightness, and the rods give us high gain, high sensitivity, but black and white vision. So when we are outside and we are dark adapted, we are seeing primarily with our rods, which means we don't have color vision. If you're in a really dark situation, you're well outside of the city lights, and you're looking at the sky and you see a white kind of glow on the northern horizon, that might be aurora. But the way to answer the question is to pop up your camera and take a picture of it. The reason that works better than your eyes is because you can set the settings so that it is collecting light for 1 second or 5 seconds or 10 seconds or even a minute. And when you do that, you're collecting a lot of weak light that adds up to a sufficiently bright image that then you can look at it on the screen of your camera and say, wow, that's what is out there. I don't see that with my eyes. You only see it with your eyes in true color when it's quite bright. That's always disappointing because you want to see it with your eye. Okay, this is one that we haven't talked about yet. This is a really important one. What is causing the increase in northern lights activity and brightness, and why is it occurring over wider geographic areas and lower latitudes? What is causing this increase is that we are on the upswing part of a solar cycle. So the energetic particles that come out from the sun follow a cycle that is at least approximately 11 years. That 11-year cycle goes through a minimum and a maximum and then goes back down to a minimum. We are right now, we are very close to maximum. Solar max, I think, is supposed to be 2 years from now. Why is the northern lights activity occurring over wider geographic areas and lower latitudes? That's because we're getting more and more strong storms corresponding to being up on the peak of the solar activity cycle. This is where I have to pause and say, probability theory is a funny thing. Sometimes we think that if something has a low probability of occurring, it will never occur. That's not what that means at all. It means that it's not very likely to occur. You can, and I have seen repeatedly, really great auroral displays, even at solar minimum. It's just less often. This question is really having to do with, gosh, we seem to be hearing about it all the time right now. That's because we're in a very rich, active period right now, and the sun has been fairly quiet for a long time, partly because of this 11-year cycle, but also the previous cycle was weaker than expected. The level of activity in the previous cycle was about, at its peak, was only about half of what it is right now, which means it's more than 20 years since we've been at a really good peak. So yeah, this one, are there any major differences between the Aurora Borealis and Aurora australis, which means the northern lights and southern lights? And the short answer is no. They're in fact mirror images of one another. In other words, the charged particles are coming in and interacting with the magnetic field of the Earth, and some of those particles get sent to the North Pole and some of them get sent to the South Pole. So we have a simultaneous, essentially identical display happening at both poles. I think that's it. So